Muy buenos días, muchos saludos para todos los asistentes.
Good
Gracias por
morning and greetings to everyone to this second day.
Vamos a iniciar antes de entrar en materia con el evento con
We're
algunas.
going to start with some important indications regarding the interpretation service that we will provide.
Information about translation service that you can find on this Zoom platform. Para eso vamos a invitar entonces a Fiona.
We will invite Fiona, who is responsible for the service, to give you some information. Go ahead, Fiona.
Muchas gracias, Germán. Buenos días. Thank you, Germán. Good morning. En la parte baja de su pantalla verán que la interpretación ya está habilitada. Aparece con el nombre de interpretación, con un icono de globo. Así que si ustedes necesitan interpretación de inglés a español, por favor hacer clic en ese botón y luego escoger la opción de español. De esa manera, cada vez que necesiten interpretación del inglés al español, o cada vez, mejor dicho, que alguien hable en inglés, ustedes automáticamente escucharán la interpretación del inglés al español. So once again, good morning or good afternoon. Interpretation has already been enabled, so it will appear as a button called interpretation with a globe icon at the bottom of your screen. So if you need interpretation from Spanish into English, please go ahead and click on that button and select the English option. That way, whenever somebody speaks in Spanish, you will automatically get the interpretation into English. Thank you very much. Muchas gracias.
Muchas gracias, Fiona.
Thank you, Fiona. Let's continue with our event, but we'd like to inform you that this is also being transmitted through Facebook and YouTube, and on the chat you'll find the links. So then I'd like to officially welcome you all to this second day of the annual conference called Metrology for Digital Transformation. My name is Germán Romero from the National Metrology Institute of Colombia. And also where the Master of Ceremonies will be Anime from Colombia. This conference is organized by the Working Group Metrology for Digital Transformation of the Inter-American Metrology System, SIM. Before starting with the presentations, it's important to keep in mind the following indications. I'd like to inform you that this is being recorded from beginning to end. The videos, you will be able to find them on the webpage where you registered your participation. Please remember to keep your cameras and microphones off so that the event can progress in the best way possible. I'd like to remind you also that all questions during the event can be entered into the chat, and once we have concluded the topic or after the speaker concludes, then we will answer your questions. When asking the questions, don't forget to say who they are for, and of course your name. For those people who are seeing us watching from social networks, you can also put in questions in the chat. At the end of the event, we're organizing a survey. So now I would like to formally start the event, inviting Diego Corpa to say a few words of welcome and for the inauguration of the second day. Mr. Corpa is the Vice Chair of the Working Group Metrology for Digital Transformation of the Inter-American Metrology System, SIM. He's a metrologist in the Flow and Volume Department of the National Industrial Technology Institute of Argentina, as well as being responsible for promoting the certification of digital calibration certification. He also is responsible for quality management. Mr. Corpa, it's a pleasure to have you with us, and please go ahead. Thank you very much, Germán. Good morning, everyone. And welcome to the second day of the M4DT Conference 2021. My name is Diego Corpa. I am the co-chair of the working group. I think I hope yesterday was interesting for you. But before commenting on the agenda, I'd like to invite you to write any questions in the chat. So questions for presenters, you can ask them during the presentation and not at the end. So we will have 6 presentations on legal metrology, laboratory automation. And the first of the talks will be Carlos Gallardo from Inmetro, who will be talking about what's necessary to unlock digital transformation in legal metrology. What do we need? And then Lars Arendt from the Pershman Laboratories on digital transformation for customer service and process optimization in calibration laboratories. Then Patrick Abbott from NIST USA. He will be speaking of increasing throughput and accuracy and mass metrology through systematic automation. Then a talk on digitization for the pH method by Victoria Gelabert from Latu, Uruguay. After that talk, it will be 16:35 UTC, and we'll have a short 10-minute coffee break. And then a presentation on the implementation of a scientific metrology cloud kernel as a byproduct of the digital twins by Hugo Gasca. Aldo Garcia, first steps towards the development of a digital twin. I hope that the talks meet your presentations. Thank you. Thank you, Mr. Corpa, for your words of welcome. And we will start then the second and last day of this conference, Metrology for Digital Transformation. So we're going to be have a block on cloud systems. Rodolfo Sosa is the head of a division from the National Metrology Institute, Quality and Technology of Brazil in Metro. So welcome, Dr. Sosa.
Welcome, everyone. We start the first block of the conference with the top cloud system. We remind you that you can ask your questions in the chat during the presentation. At the end of the presentation, the speaker will answer all the accumulated questions from our webpage, social networks, and those on the Zoom platform. We remind you that for time reasons, we have shortened the resume of our speaker, but we invite you to visit the event website where you can obtain more information about each of them. Next, I introduce Dr. Gallardo, who will present the speech entitled Unlocking Digital Transformation in Legal Metrology. What do you need? Carlos Gallardo is a researcher at Inmetro. He also worked at NIST as a guest researcher from 2019 to 2020. He earned his PhD in computational physics from University Federal Fluminense in 2010, and his research interest includes data analysis and mathematical modeling in interdisciplinary applications. Nowadays, he is working on models and methods to analyze security weakness. Gallardo, please go ahead.
Okay, let me share my screen. Okay, everyone can see that?
Yes, we can see.
Okay, that's great. So thank you very much for this invitation. I'm delighted to be here and share the Inmetro experience on digital transformation in legal metrology. So this is the outline of my presentation. I will start defining legal metrology and digital transformation. Then I'll tell how Inmetro gets into digital transformation. I will discuss the critical components in digital transformation in legal metrology, software assurance, and internet digital infrastructure. Next, I will present how digital transformation impacts Brazilian legal metrology. Finally, I will briefly discuss what might come next with the legal metrology cloud. So first, definitions. As OML defines, legal metrology is the practice and process of applying a regulatory structure and enforcement to metrology. To understand legal metrology better, let's think about one activity, buying gas. When we buy gas for our cars, we trust that we get what we pay for. The amount displayed by the instrument should be the volume dispensed by it. Here, three critical properties must hold: accuracy, the measurement agree with the corresponding standard; reliability, the measurement result should not be affected by external variables, such as weather; and security, the measurement result was not maliciously manipulated. Accuracy, security, and reliability of regulated measurement instruments are the legal metrology goals. The most recent OML bulletin has an article by Dr. Florian Thiel that defines digital transformation as the process of using digital technology to create new or modify existing process, service, culture, and customer experience to meet changing business and market requirements. We have two paths ahead from this definition: to apply digital transformation to legal metrology, and to have legal metrology enabling digital transformation. I want to state that this presentation is mainly about the first. So let's take a look at the process in which we could apply the digital transformation. Regulations, which contains technical requirements, are the ground for other four processes in legal metrology. Type approval, a legal decision that a measurement instrument type complies with the relevant requirements. Verification, the action of checking that an instrument in use complies with the approved type. Supervision, the observance of metrology regulations. And examination of measuring instrument to demonstrate some metrology property, for example, to testify in court law. Now, I have defined metrology goals and process. I bet you should wondering the next steps, something like applying digital technologies over the legal metrology process to achieve such goals. Unfortunately, that was not what happened in Brazil. It was a much more sinuous path. Inmetro discovered itself in a digital rabbit hole 14 years ago. In 2007, many customers filed a complaint about electricity bills. At that time, new electronic energy meters were authorized by the Brazilian Energy Agency to be installed without being type approved. Luckily, Inmetro had a couple of cybersecurity researchers that solved this issue. After several months of investigation, they had discovered that 5% of those instruments had huge errors, and the cause of those errors was software bugs. Unfortunately, bugs were not the only problem. Instruments lacked a standard communication protocol, and connecting with them became a troubleshooting exercise. For example, a vendor presents the following solution to access legally relevant data in the instrument. First, a handheld communicates with the instrument. This handheld sends message to a piece of hardware that's connected to another piece of hardware that finally sends information to a computer. The digital hole was even deeper. Instruments also suffered a lot of unauthorized modifications. This slide shows an example found in a Brazilian gas pump. On the left, we have the original circuit from a gas pump volume sensor. On the right, we have a counterfeit one. The counterfeit can behave exactly as the original one, but it also has an optional feature. It can deliver less gas than the pump display, creating an unfair trade. As you can see, they are pretty the same circuit, except for the microcontroller they use. This kind of memory replacement attacks is not limited to gas pump. They could happen with any built-for-purpose instrument, such as utility meters, grain moisture meters, and no automatic weighting scales. Here, we show another kind of unauthorized modification. A small chip was inserted between the sensor and the CPU of a gas pump. This small device enables the same optional feature as before. The pump can deliver less gas than it displays. The instruments manufacturers and the attackers already did their first step in digital transformation, and Inmetro, in 2007, was lagging behind. And that happened because Inmetro didn't realize the importance of the new technology in legal metrology. Failing in our legal metrology goals had revealed what we are missing. In some sense, we're lucky because our failure was noisy. Otherwise, we could lag even more to understand our needs in digital transformation. We started by hiring cybersecurity researchers, followed by some training in digital forensics. We also reviewed our regulations with software security requirements and created a digital infrastructure that mitigates unauthorized modifications. Let's talk about the software assurance. Inmetro reviewed its metrological regulations to add software requirements to mitigate bugged software in type-approved instruments. To do that, we followed international guidelines in legal metrology, such as OML 31 and WELMAC 7.2. The diagram shows the year of the reviewed regulation by instrument. Its ongoing work that started with the electrical energy meter in 2009. Our regulated instruments go through a conformance testing, including documentation review, white box testing, and black box testing. Nowadays, Brazil has 8 laboratories to perform those security tests, 2 labs at Inmetro, 5 at universities, and 1 in a private company. The digital infrastructure need for legal metrology is no rocket science. It is the technology that enables today's internet using well-known cryptography. The challenge lies in how to adapt the technology to legal metrology needs. Warning, the digital infrastructure I will be describing is not designed to be applied as a whole to all regulated measuring instruments. In Brazil, we only use the entire infrastructure to gas pumps, while some features are applied to all instruments. Our regulated measuring instruments in Brazil must provide a software integrity verification protocol to mitigate memory replacement attacks as the one we show. Inmetro recommends a challenge response protocol. Let's suppose you have an auditor that's checking a gas pump. The protocol starts with the auditor create a challenge for the instrument. It's something that the instrument could not know in advance, such as a random number. The instrument computes a response that's a function of the challenge and the instrument software, and send it back to the auditor. The auditor, who knows the approved software, represented by the blue box with 1s and 0s here, checks the response by performing the same computation the instrument did and compares it with the response sent by the instrument. If they are the same, the instrument has the approved software. Inmetro enforces through regulations that high-risk instrument must digitally sign every measurement they produce. Public key cryptography allows digital signature through a pair of keys, one public, one private. Given any string M, which could be a measurement data, the party can use its private key to compute S, the signature of M. Given M and S, any party with access to the public key can verify S is the signature of M created by the owner of the corresponding private key. Without the private key, it's unfeasible for any party to create S. Digital signatures provide authenticity and integrity. An auditor can run the verify sign algorithm to ensure that the measurement result is authentic and was not maliciously manipulated. So, after a measurement, the instrument signs the measurement results M and sends M and the signature S to the auditor. The auditor runs the verify algorithm to ensure the authenticity and the integrity of the measurement data. The critical question here is, how do the auditor trust that the public key belongs to that instrument. A public key infrastructure, or PKI, can be in place to associate public keys with identities by creating digital certificates. The idea behind a PKI is simple. In a PKI, you should have at least one certificated authority with a public key that all parts trust. The authority certifies instruments by signing their public keys concatenated with appropriate identification. This pack containing IDs and public key signed by a CA is known as a digital certificate. Anyone who knows the CA public key and has the instrument certificate could validate if a particular public key belongs to one specific instrument. In Brazil, to be a CA, the institution must comply with several regulations issued by the National Institute of Information Technology. In March this year, Inmetro became a certification authority for metrological objects. The integrity verification, the digital signature, and the digital certificate are great tools. However, they will not be feasible to implement across several instruments with different manufacturers. A standard communication protocol must take place. It's the last piece of technology we need to unlock digital transformation. Inmetro established a standard serial communication protocol that manufacturers could implement over protocol stack, such as TCP/IP, or directly over the physical layer. Also, Inmetro requires that high-risk instruments implement Bluetooth technology, allowing users to verify their measurement results. The protocol defined by NIT since 20 is a small set of commands to allow software integrity check, retrieve information such as audit records, identification, instrument digital certificate, and measurement results and their digital signatures. Now let's put all those bricks together and see how they could improve metrological verification surveillance. Again, let's suppose you have an auditor that's inspecting a gas pump. First, the auditor gets the CA public key. The auditor starts a session with the instrument using Inmetro's standard protocol. The auditor requests the instrument digital certificate. The auditor uses the CA public key to validate the instrument certificate. Then, the auditor runs the integrity verification through the challenge response protocol. Next, the auditor performs a measurement and collects a digitally signed measurement result. They verify the digital signature. And the auditor collects the audit logs and check for any suspicious activity. For example, too many changes in calibration parameters. With Bluetooth technology, any customer with a smartphone could connect to the instrument, requesting measurement result data and verify the digital signature. The smartphone could transmit the requested data and GPS location to Inmetro, creating a database for further surveillance operations. Let's now look at the big picture of the legal metrological control. In this diagram, we have different processes. From left to right, we have the type approval, instrument production, verification, and surveillance. During the type approval, the vendor interacts with the accredited laboratory to demonstrate that the type and its software comply with the regulations requirements. Inmetro stores the type approval information, which include the manufacturers, the type, and the respective software identification. During the production, for each instrument, the manufacturer must request a digital certificate from a CA. The certificate contains information about the manufacturer, the type, and the serial number of that instrument. This information also goes to Inmetro and is stored in another database. Next, while being used, the instrument must undergo verifications. During verifications, the auditor validates the instrument certificate, executes the integrity verification, verifies digital signatures, and collects audit logs. The information is reported to Inmetro and stored in a third database. Finally, customers could help market surveillance empowered by Bluetooth technology and a smartphone. The smartphone collects information about the measurement and sends it to Inmetro. This entire infrastructure should start running in Brazil by July 22 for gas pumps. So I'm no specialist in cloud computing, but I share the current thoughts of our team. Cloud computing could be understood as computing service provided over the internet. It enables fast deployment and flexible resource. It lowers cost and improves scalability, performance, productivity, and reliability. We can have three kinds of service in a cloud computing environment: infrastructure as a service, platform as a service, and software as a service. How do we translate those kinds of cloud service to legal metrology? We foresee two scenarios. Manufacturers of measuring instruments implements a cloud computing architecture, or the National Metrology Institute enables cloud computing. In one, we are aware of 2 points. Inmetro should catalyze the interaction between different manufacturers to provide interoperability of measuring instruments and adapt the software security testing concerning a new attack surface. In two, we foresee that all data collected from the digitally transformed legal metrology could enable business that integrates such data to online platform. For example, a gas station could have ratings on Google Maps based on how much surveillance attention they receive from customers. Also, all collected data could be available as a platform itself. Inmetro should be aware of the associated privacy risks. So, to unlock digital transformation, we hired cybersecurity expert, reviewed regulations, created digital infrastructure, and integrate metrological service in today's technology. I feel deep honored to present Inmetro Works to such an audience. Thank you for this opportunity.
Thank you, Gallardo, for your speech. Excellent. If someone has questions, I ask to put on the chat, and I will give to Dr. Gallardo. And we begin the block of the questions. The first one, wait a moment. The first one from Siegfried Hackel of PTB. Who is the responsible body for the CA?
Oh, so can you hear me?
Yes.
I mess up a bit with the interface here. So in Brazil, the responsible body is ITI, that's National Institute of Information Technology. And for that point here, so it's the root AC, right? So we have Inmetro as the first level AC now, and Inmetro will be the root for all metrological objects. So Inmetro itself, we will not issue digital certificate to instruments. We will have under Inmetro, in another level, the second level, other ACs like private companies that could issue the certificates to the measuring instruments. I don't know if I really answered the question, but I think that was it, right?
Okay, I think it's answer. There is another question. Do you have a timeline in mind for the widespread implementation of such a scheme? Okay,
so we can think like we discovered the first problems in 2007, and all that problems we found with the gas pumps starts at 2012. So more or less we take like 10 years to put everything together And I can tell you that the tough part is to talk to vendors and manufacturers and convince them to change their project so we could enable such technology, right? So you have a lot of private companies that must agree about changing their product. So this is costs for them, right? And this is a long journey, right? Showing, you have to do a lot of field work, like showing that the frauds exist, we have real problem, we have real attacks, and we really need to change all the landscape.
And the solution that we propose could be effective for prevent fraud. Is there any more questions on the chat? Let's see.
Just one more point about the timeline, right? So it's 10 years to start it, right? Now we have to rotate the entire field, right? All pumps that are installed should be replaced by a new one. So until you get all the technology replaced, this is more 10 years, right? So the real time scale here is like 20 years.
And we also consider to use in other biological equipment.
Yeah, that's true. The gas pump is just our first attempt because all the frauds, all the attacks we have on it.
There is another question. This is interesting, very interesting. Inmetro accepts whether the manufacturer has a verification of software issued by another country based on OEML D31 or only certified by Inmetro?
Yeah, that's a very good question for this audience. No, we don't. The instrument must be certified by Inmetro's regulations because it's like Brazilian law. Right now, we don't have a law to create such an interface that we could accept certified instruments from other countries. So we need to go through the entire certification process in Inmetro.
Okay, I think that this is the last question. Thank you, Dr. Gallardo. I will return the speech to
The pleasure was mine.
Thank you.
Muchísimas gracias al doctor Carlos Gallardo y al doctor Rodolfo Sousa por este excelente tópico que nos acaban de mostrar. A continuación vamos con el siguiente tema sobre automatización de procesos de laboratorio. En esta oportunidad nos estará acompañando el doctor Alexis Balki como moderador. El Dr. Balki es consultor peruano-alemán especializado.
Dr. Balki is a consultant specialized on quality infrastructure, policies for development, agricultural development, that is, and trade aspects. So welcome, Dr. Balki. Good morning. Thank you, Germán, for your introduction. Welcome, everybody. And we're now going to begin with the second block of this conference, Laboratory Process Automation. So we are going to have three panelists who are going to share their experiences. And I would like to remind you that you can ask your questions. There are going to be three panelists. So please, when you write your questions in the chat, mention or explain who these questions are for.
The presentation titled Digital Transformation for Customer Service and Process Optimization in Calibration Laboratories. Lars Arendt is a mechanical engineer and business administrator. And since 2009, he worked at Persman Calibration in Germany, occupying different positions such as sales representative, field tester, laboratory director, sales director, and general manager. Today, he's going to show us the advances in the digital transformation of the Persman company, which is one of the most important calibration companies in Germany and performs thousands of services per year. Engineer Lars Arendt, please go ahead.
Yes, thank you, Alexis. Yes, just let me use the screen. Yes. Can you now see my screen?
Yes, we can see your screen. Not in a presentation mode at the moment.
But now, right?
Now, yes.
Yes. Yeah, thank you for the possibility to give you a few information about our company and how we do process automation with digital solutions. A very few figures to our company. We are in the south of Germany. We have about 135 employees. 10 people work in the sales department and 15 inside the office, and 5 work as traveling salesmen on site. And we have about 50 people testing instruments in our laboratory. So 50 people performing the calibration. These figures are very important for us. We are accredited according the 17025 by DAKKS, and we perform about 400,000 calibrations per year, and 100,000 calibrations are according DAKKS, so accredited calibrations. We're accredited for length, pressure, electrical instruments, force and torque, also temperature, and we are accredited for calibrations in our stationary laboratory here in Braunschweig, and in situ, and also for mobile calibrations. Most of the calibrations are concerning instruments in length. Yes, we have about 15,000 customers in Germany, and 15,000 customers, 95% in Germany, and 5% in Europe, in the rest of Europe. So this causes some trouble in our laboratory. We have 15,000 customers, and with 800 customers, so less than 10%, we have a turnover of 70% a year. So we have a big number of very small customers. And these small customers have always the same questions. If they do not know us, they ask us, are we able to do a calibration of a certain item? They ask us if we are allowed to do that. Allowance means if we are accredited or not. Of course, they're interested in the price, and they ask us to send an offer. But not these 800 customers, but the rest of the 15,000. So this is a very big workload for our company. So the challenge for the sales department are these questions. The questions, what kind of instrument has to be calibrated? The customer has a name for a certain item, maybe we have another name for that. So it's always a discussion about the type of instruments. For us, it's a question, how is it possible to answer very quickly? Because all of our customers are in a hurry. How to reduce workload for our sales department at the end to save money, of course. Then how to offer the service 24/7. So at the moment it's evening in Germany. I'm the only person working here. So if you now ask us for a price, no one can help you. So the question, how could we offer our service to give price information, for example, 24/7. And how is it possible to offer self-service for our customer? Because we have to answer all these questions, and it would be very nice for us if the customer could get an answer by themselves. Yeah, the solution, we developed Calibration Scout. That is our name for that, what I explain now on our website. And with that, we installed a self-service for our customer. So we optimized the process in this way. If you move to our homepage, there's the Calibration Scout. In this Calibration Scout, you can enter some kind of item, for example, caliper. Yeah. If you enter that here, then you can press enter, and the software will give you detailed information about all the several items we are able to calibrate according to DAKKS or some other procedures. We have not only the item, we have also an article number for that. We have a price for several measurement ranges, and all these information you can receive on this website. So the item itself, you can have a closer look to a picture to verify if it's the correct item. So we have photos for nearly all instruments we calibrate in our laboratory. We have a price information. This is depending on the range. So for each several article number and range, you have a price information without discount. You have some information to the calibration procedure, and you have a shopping cart here, so you can select the several services, and at the end you have a price list. So if you have 24 items, you can select these here in our, it's not a shop, but in our Calibration Scout, and at the end you have a price list. You can also change it in a delivery note, and you can send us this list to ask for a quotation. So if you are interested in some kind of discount, for example, or the time of delivery or time of performing the calibrations, then you can ask for quotation. This reduces the amount of workload, and we work with this since 1.5 years. And at the beginning of this year, we added the price. So in the first time, we checked if this service is working, and after we installed everything correctly, we put the price in that list. This is for us, it's a very easy digital service to optimize the cells, the process of the cells department. But this is only for new customer which are interested in our service and want to get some information about the price or want to develop a delivery note. So our problems at the beginning, what kind of our questions, what kind of instruments, how to answer quickly, how to reduce workload, to offer that 24/7, and how to offer self-service. These questions we answered with this solution, and it's very cheap. So it was a very good investment for us to do that. We use that for new customer. So you can go on our website. You don't have to log in yourself somehow. You just can use the Calibration Scout to receive information. Our main focus is, of course, on customer we work together with. So the next question I want to answer is how to optimize the whole process from the customer to our laboratory and back to the customer. We call that end-to-end with established customer. Yeah, and therefore the solution is very easy. At the end, the solution is to connect our laboratory directly with the customer. And we started that years ago with a vision that was the start of the development of that solution. We had this idea that you could be in some kind of audit wherever you are. For example, on that windmill, and if you have to work there, and you could use a torque meter, for example, then the question could be: is it allowed to use that? Is it calibrated or not? And the idea was to put a code on that item and to develop a software with that you can scan the code and can receive an information immediately. For example, on your smartphone, that if you scan that, the result could be okay because it's calibrated in between the interval and the result is okay, or maybe it's not okay, of course. That was the vision, to develop something that this could be work. The second was that a lot of our customers use this drilling or milling machines, and they always have the question, if they use this, for example, a plug gauge, that the question is, am I allowed to use that or not? And directly before they use it. And we have the same solution, that we have some kind of handheld computer, smartphone, or something like that, that we have our code on this plug gauge, and then you can scan that, and the software will show you if you are allowed to use that or not. Yeah, how does that work? So we have our customer and we have our calibration laboratory, and the customer have to send their instruments to our laboratory. In 95%, a few instruments we calibrate on site, but normally they send the instruments to our calibration laboratory. Then we do the calibration with a software we developed in-house. It's called Trendic. It's a trademark of our company. We do all 400,000 calibrations with this calibration software. So all these data are inside that. And then we developed a window for our customer, a window with this, he can have a look in our calibration software. So he has a direct connection, of course, with a firewall, but a direct connection to our calibration software. And he has a software. So the window is a GUI. With this, he can administrate his own instruments. And so at the end, he has a look on our database. We fill in the database with the calibration information, of course, and he can give some information to the database as well. For example, he can put new instruments in that database. Then he can send the instruments to us, and we know the instruments before they receive our calibration laboratory. What are the advantages for our customer? The benefits are, he has a very easy view to the certificates. He can do that with the computer, with the tablet, or with a mobile device. It doesn't matter. So wherever he is, he just needs contact to the internet, and then he can have a closer look to his certificates. He has the software to do the complete administration of the instruments. Also, if he has an audit, he can show all details to his instruments. He can create a delivery note to send the instruments to our laboratory, maybe also to another laboratory, but it's the best, of course, in the process if he sends the instruments to our laboratory. He can create the delivery note per mouse click. So he can select the several instruments in this administration software, but he can also scan the instruments. So we developed a small sticker, and this sticker is on all the instruments we calibrate. We put this very special sticker on the instruments, and the sticker, you can scan that if you have a mobile with you at the moment. If you scan that, you should see a number. The number of this is PECAL for our calibration laboratory, and then a number. This number is combined to the data set in our database. So each instrument has a ident number, of course, a visual inspected ident number, and our sticker and our database connects this sticker with this ident number and the item itself. And if you scan this with our calibration software, then with this administration software, if you scan that, then you see all information you are interested in. And this software includes not only the instrument, it includes also the article number for the calibration we performed, and also a price. So if a customer works with us, then he has all information to his calibration, to his instruments, and to the calibration certificates, and the price in this administration software. And this here is for cost-free. So then he can use a function to receive a reminder of due instruments. So he could receive automatically mails from the system with a list of due instruments to be sure that the instruments will be calibrated. And he can change this list of due instruments directly in a delivery note. You can also upload certificates of other laboratories. So it's not only for the calibrations of our laboratory. And you can assign instruments to work orders per scanning. So if he scan this code with a mobile device, for example, then he can scan afterwards a work order number and combine both in a calibration software. These points, reminder of due instruments, upload for certificates of other laboratories, also this assigning instruments, that is not cost-free. So for this, we charge our customer. And he can also download his certificates, for example, as a PDF or as a data file. And this could be later on, we are working on that, this could be the DCC. But there are not only benefits for the customer, there are also benefits for our company. And I want to name them. So we are able to copy this digital delivery note into an order. So if he sends us, customer sent us maybe 120 instruments, then we just have to check if he sent all the instruments which are on the delivery node. And if that is okay, then we can press a button and this digital delivery node become an order with article number, with price, and so on. And with that, we can create the work order for our tester absolutely automatically. So we save about 80% of the workload in our receiving department. They are working at the moment, they are working 16 people, and the more customer use this solution, the less work order we have. We can use the administration data of our customer. Administration data as the interval, for example. So the customer do not have to write the interval on the delivery node. He just has to put in these data in this administration software, and we can use it both. Also some information at storage location of the customer and the name of the staff of the customer, if he wants to have these information on the calibration certificate.
Excuse me, Lars, 2 minutes? 2 minutes?
2 minutes, yes, I'm nearly ready, yes. We can reduce the cost of the print of the certificates and the delivery of PDFs and so on, because the customer can download that by themselves. And we receive the instruments again because the customer use the reminder function. Very important is that we strengthen the relationship with the customer. If we and our customer, if we both use the software and the customer is satisfied with this solution, then we work tougher together, and that is very helpful for us. And we increase the sales and earnings with the SaaS model. So the customer has to pay for special services. So we have a turnover, and we have not only earnings in the process, but also earnings with the software. So we reduce the laboratory costs with a reduced amount of work. We reduce complaints, of course, and increase quality. We strengthen the relationship, and we have sales and earnings. Thank you.
Thank you very much.
Answer you some question.
Thank you very much, Lars, for your excellent speech. There are a lot of questions in the chat. We will come at the end after the others. If you can have a look at it.
Yes, I will do. Yeah.
Okay. A la audiencia.
So to the audience, I would like to remind you that if you have any questions, please send them in through the chat.
Now I am going to introduce our next speaker, Patrick Abbott, who will present a speech entitled Increasing Throughput and Accuracy in Mass Metrology Through Systematic Automation. Patrick Abbott is the leader of the Mass Calibration Project at the National Institute of Standards and Technology, NIST, and has been a member of the Mass and Force Group for 14 years of SIM. For over a decade, Patrick has been involved in NIST's contribution to the international effort of redefinition of the kilogram. Prior to joining the Mass and Force Group in 2007, Patrick spent 15 years in the NIST Pressure and Vacuum Group, where he was responsible for dissemination of the Pascal in the high vacuum regime. Patrick holds a BS and MS degrees in physics. Patrick Abbott, please go ahead.
Thank you very much. I'm very pleased to be here. And hopefully I am sharing now.
Yeah, you are sharing your screen.
Yes, very, very
not
good.
only the presentation.
Yes. Okay, let me just start.
Now you share the presentation.
Yes, very good. Okay, so thank you once again for having me as a speaker here. It's a pleasure to be here, and it's been a very good conference so far, wonderful presentations, and I hope that you will be just as edified by what I have to say today. And it's interesting that I come after Lars. Lars gave a nice presentation on what a calibration company faces in this time of digital transformation. Many customers wanting to schedule people, allow them to do their own things. But the thing that I really want to emphasize is he's dealing with lots of people. The presentation that I am going to give talks about what we do at NIST. And of course, we're the NMI for the United States of America. So we have far fewer customers, and our requirements are a little different in that regard. But in the same sense, Lars and I both are dealing with this digital transformation that is going on and represents, I believe, an evolution in metrology throughout the world. So again, I want to say that this evolution is just as big in the digital transformation as, say, going from instruments from years ago. Here on the left, I show a mass comparator from the early 20th century, and you see a fellow over here looking through a telescope to read the deflection of a pointer so that he can do his mass measurement. Very far from being automated. Whereas on the right, we see a completely different type of an instrument, totally automated, where there are several masses in a little magazine, and each mass can be picked up by a robotic arm and put on the mass comparator. So this revolution is sort of similar to the one we're seeing right now in the digital transformation, and why we're having this conference. So metrology is greatly affected by everything that we're talking about here. All right, so let me continue. Just a brief outline, an introduction, defining a challenge, planning a solution, coding a solution, where we're going to use software to help us to improve our process. Then I'm going to look at how we assess the progress that we have made, and then looking at some future plans that we have. And again, keep in mind that we are an NMI, and we are dealing with far fewer objects and far fewer staff than many commercial companies. Okay, so first of all, some goals by way of introduction. What would automation of laboratory process do for us? Well, we're in mass calibration, and I'll talk a little bit about that, but not too much. But first of all, what we want to do, I think, and I've highlighted very important things in yellow, is to improve throughput of calibration items. And when I talk about items, just to give you some tangible representation, it's something between 1 milligram and a 50 kilogram object that people use as mass standards. We have a much broader range that we calibrate, but for now, in our automation, we do 1 milligram through 50 kilograms, so keep that in mind. We would like to standardize some sort of a software platform that we will use in doing this automation. And by standardize, I'm not talking about some sort of a legal metrology thing. I'm talking about making it uniform throughout our particular laboratories. We'd like to eliminate human data editing and the mistakes that go along with them. I think everybody is agreed that we need to get rid of that. I'd like to make calibration systems remotely accessible to accommodate, for instance, operators who aren't on site of the calibration. In this time of the worldwide pandemic, that has been an acutely important thing for us to be able to have. And I think the biggest thing is the following bullet, where we talk about storage of all data in an electronic database, which is something that we have only partially had up until now. And finally, what we've heard so many reports on so far in this conference is to prepare for digital calibration reports of some type. There is no official policy yet from NIST regarding how we are to do this. Everyone is sort of preparing and in preparation mode. And so we are joining right in with that effort. And as Dr. Henkel mentioned yesterday in his excellent presentation, this is something that we can all contribute to. Okay, so just a quick reminder of what it is that I do. I'm a mass metrologist, so I'm in a laboratory most of the time. And our entire work begins with the realization of the unit of mass. And it starts with a kilogram and its realization, and goes along through representation and working standards, and then creating transfer standards, and finally disseminating that unit of mass out to customer laboratories. And from the customer laboratories, those measurements go out to other laboratories usually, because for the most part, NIST is calibrating secondary customer laboratory instruments. So they are disseminating things that we have calibrated for other laboratories to in turn use. So NIST has a very large leverage for its calibration services. We calibrate one artifact, and it multiplies into many, many, many uses. One other point that I'd like to make, again in yellow, is that as we seek to automate this process, automation must not compromise the quality that we offer to clients. All right. So again, by way of introduction, mass metrology at NIST, our services range from 1 milligram to 27,000 kilograms or so. We serve mostly secondary calibration labs from other states, the military, pharma, and private industry, perhaps making 150,000 US dollars per year in income. More to the point, in our laboratories, we have 11 automatic mass comparators that range from 1 milligram to, that should say 6 grams to 64 kilograms. It has a very a limitation, a resolution of 1 milligram, I should say. Among those 11 instruments, there are 6 4-position and 2 6-position carousel instruments. I'll show you that in a minute. And there are 3 robotic mass comparators of the type that I showed you in my introductory slide. So just to give you a better feel for what these automated mass comparators look like, first, let's talk about what we mean by an automated mass comparator. And I've made a little definition here. That an automated mass comparator is an instrument that can select single or multiple weights to be compared in a predefined sequence. The gathered data consists of mass differences between standard and test weights, and then these differences are used to determine the masses of all the weights tested. And of course, environmental variables like temperature, air pressure, and relative humidity are also collected. On the left, we have a so-called 4-position carousel where 4 different weights can be loaded. And the job of this carousel is to rotate a given mass over to the weighing pan of the comparator whenever it needs to be weighed. So that's great. It's all automated. It can be set up in advance, but it has a limitation of only 4 at a given time. That's in contrast to the other type of automatic comparator that we have, and that's a robotic comparator that uses a magazine that is filled with as many as 36 weights, and then a robotic arm to pick those weights up and to automatically place them on the mass comparator weighing pan. So that's what I mean about mass comparator. Just a very brief idea of what sort of data we get. There are predefined sequences of weighing differences that are done. And each time we weigh something, all of these things are recorded. Of course, the time and which mass it is that is being weighed, the raw reading from the instrument, and also the pressure, temperature, and humidity, which are used in final calculations. And then after the comparison between two masses is made, the difference between those two masses is generated. And this is what is ultimately used in the calculations. So this is only what I've shown you. These four measurements is only for one simple ABBA comparison in which two masses are compared against one another. And a complicated comparison may have 8 or more weights, and many of these, maybe as many as 100 or 200 different comparisons if you're repeating the series. So the bottom line is a very large amount of data is collected to be analyzed, and of course it needs to be controlled. Okay, so what is our challenge then with automation? Well, in automation, each comparator, before we started all of this, each comparator is a standalone instrument with a dedicated computer. And that's difficult to deal with if you have a different system for every single instrument. We have 11 of these. It's difficult and time consuming to teach new staff. There was no common software or platform for our comparators. Data files required extensive editing prior to analysis. You can see I've added little frown emojis to tell you the things that really bothered me and us as we were doing this. We had an old Fortran analysis program that used a DOS shell, one file at a time. It was very, very slow, so that gets a frown. And the mass record keeping, the standards record keeping was mostly in paper form, although we did have a non-centralized spreadsheet to do this. Very difficult to document in our quality system. And again, human editing created lots of opportunities for mistakes in final reports. So this is just very good motivation for automation. Now, when we planned the solution, we wanted to look at and analyze our entire measurement and analysis process from the start to the finish. And that involved identifying steps common to all measurements and identifying processes that are unique to individual comparators. Some things are the same, some things are not the same. One of the most important things I felt was to give software a similar look and feel regardless of which comparator people were using. So a new staff member didn't have to go to a completely different looking software setup. They would all be more or less the same, or at least familiar. We wanted to design a seamless route of information from setup to the presentation of results, and most importantly, minimize the human interaction. Not to minimize human contributions, but just the interaction with data that might compromise the integrity or quality of the final result. Finally, we wanted to design an electronic database that provides input parameters, stores results, and could really be a record of everything that we do. And one of the things that we owe to the people that follow us is to have a very good collection, demarcation, and storage of all that has gone before as pertains to the metrological process being used in the calibrations, and a database facilitates this greatly. Finally, keeping it simple, and that's a challenge with all of the steps in the process that we have. Keeping it simple was really going to be a challenge. Okay, just a flow chart to show you. I'm not going to go through this in detail, but I do want you to know that as you see this from start to finish, this process going from the pre-calibration preliminary activities to the final report, each one of these individual boxes has its own flow chart. So I've only shown you a small 30,000 meter view of this process. There was much, much more to consider. So the exercise of going through our entire process helped us to learn about what it is we do and how we could do it better. So I think it's valuable for all laboratories to do this when considering digital transformation. Okay, so what about the solution to our problem? Well, we're going to use some sort of software tools. And those tools turned out to be the following things. an SQL server database, and LabVIEW object-oriented programming. Now, many of you are familiar with LabVIEW, but you may not be familiar with the fact that it has object-oriented programming capabilities. It does, and they work very well, especially in this application. So I encourage you, if you're doing this type of thing in your own laboratory, to investigate its abilities. We also had a professional programmer and IT specialist from within NIST working with us full time. And one of the goals of all of his work was to have identical workstations at each computer, or excuse me, at each comparator, again, in the name of uniformity, that would be a 64-bit Windows 10 platform and a laptop computer with a docking station and a 61-centimeter display. So if this is sort of the uniform display, then it would be much easier to train staff when they weren't always having to see different types of hardware and then different types of software. So that's very important. I'd like to show you now what a graphical illustration of the solution looks like. So eventually what we created was a custom software suite that has at its center this SQL server database that we created. And the SQL server database maintains a bidirectional flow of information between all of the applications in itself. So you see here, we have got 4 applications. We've got artifact record keeping, comparator control, data analysis, and environmental instrument handling. So whenever something is happening, when one of these applications are being used, there is a constant back and forth exchange of information between the application and the database. This eliminates things like having to go and look up numbers for accepted values for masses or calibration coefficients for environmental instruments and so on, and put them in after you've already started. If the database holds all that information already, then all of this can be dynamically shared with the applications. Okay, just want to give you some very quick view of what we've come up with. This is what the artifact database, part of it anyway, would look like in presentation form to the user. There is a place where you select a customer, and I've grayed out all of our customers here other than NIST. And what would happen is you can filter this by the mass of the artifact or the identification number of the artifact. And once you have done that, you can then look and see, okay, this is all the information that is in the database already about that particular artifact. So we've got built-in history here that we don't have to scramble to find. And then for that given artifact, there is a list of all of its parameters, its nominal mass, its correction value, accepted correction value, its density, its volume of coefficient thermal expansion, its center of mass. All of these things are available for entry, for modification into the database. So we use this for both NIST standards and also for customer artifacts. And it allows us to have history plots and all these other things that I've just mentioned, and to share it with the software suite of applications that were created. So looking at the other application for comparator setup, it allows us to choose the instrument, a given instrument. We have 11 different comparators, and we can put in a test folder for that particular, if it's a customer calibration, put in the operator's name, save the configuration of everything. And again, all of the things that pertain to running a given calibration, the number of series you want to run, pre-runs, start delays, etc. And again, we have to tell the comparator which artifacts actually to use, and the database helps us do that. When we choose a particular customer, all of the artifacts that we have for that customer show up, and we can populate the individual positions by just dragging and dropping over onto these carousels. So this was a very nice programming feature, the drag and drop scheme that we have. Okay, the analysis part of the code is also very nice. Once all of the data is finished, it can be analyzed at the click of a button, and then all of the series are put out in tabulated form with uncertainties and graphed. In this case, you see a red graph and a blue graph, and that's because there were two different artifacts done at the same time. So it's plotting the results for both of them on the different axes. And down here, we have what every good metrologist knows is the results of the check standard to verify that your process indeed was good. So we've got all that at the click of a button. And the fact that everything up here is green, these tell us the uncertainties and the different statistical tests that are used. And the green means that all of the statistical tests were passed. So we know that this has been a good run. Down in the lower left is the summary of the results and that the mass code has put out, and this can be scrolled through to see all of the parameters that were input. So this is very nice. So to assess what we have done so far with the software and these applications, we've been able to apply it to 8 of 11 comparators so far. They are running this new software suite. One nice thing is that multiple comparators can now operate and simultaneously interact with the SQL database that we've made. This has been very, very valuable during the pandemic, when most of the time that either I or someone else from the group has run things, it's been remotely. We're working at a computer at home and controlling a comparator at NIST. Some other highlights, data on a given comparator can now be analyzed and plotted in less than 2 minutes. And previously, this was a 1 to 2 hour process that involved editing of data and possible mistakes and so on. Now it is completely seamless, no human touching the data, and it can be done in just a couple of minutes with timestamps on everything. The throughput and staff efficiency has been greatly increased. The problem that we have is not so much how do we get more income by doing more instruments, but how do we maintain our services with a very limited number of staff? So if we can increase our efficiency through software, that's a tremendous asset to us. And we've been able to do this with the software so far. And what do we have for the future? Well, we need to finish those remaining 3 comparators, the robotic software. And we would like to add some long-term statistics data mining from the database that we're creating. We heard a talk yesterday about data mining and how important it is, and we would like to introduce this capability. And we would also like to, here's some noise in the background. We would like to enable the digital report handling capability and possibly handling the XML transfer, which LabVIEW can also do. And so with that, I believe that's all I have to say. I have one last thing, is giving thanks to our NIST laboratory automation team leader, Greg Calla, and our NIST IT specialist and LabVIEW programmer extraordinaire, John Quintavelli. So with that, I thank you for your attention.
Thank you very much, Patrick, for this presentation, excellent presentation. And it's also interesting, as you highlighted, to compare the different laboratories we're talking about and the different ways how to automate. Thank you very much. I remember to make the questions in the chat. And Patrick, if you can have a look at your question also to prepare in order to have a fluent answering session after the next presentation.
Yes.
Como último tema, les presento a Victoria.
Lastly, I would like to introduce you to Victoria Helabert and Pablo Constantino, who are going to talk about digitization for the pH method. Victoria Helabert works in the chemical metrology laboratory of Lato Uruguay. In the electrochemistry area, she works on reference material development in this area specifically, and she also participates in the P2B project for aquatic project specifically. And Pablo Constantino works in the metrology department in Latu, Uruguay as well. And he's a representative of Latu and in SIM specifically. He has experience in calibration, standard maintenance, and design of instruments and measurement systems. And he's also a technical auditor in physical metrology for the Uruguayan accreditation body. Go ahead, Victoria and Pablo. 20 minutes. Hello, everybody. I'm going to share my screen. Can you see my screen?
Presentación, pero no en modo de presentación.
We can see your presentation, but not in presentation mode. Yes, we can now see it. So we're now going to talk about the digitization for the pH method. So the pH measurement, which is carried out in different ways in all laboratories. For example, laboratories use many samples, use different methods. However, the method we're going to be developing is a method which is only used for the characterization of a pH reference method. So this measurement is measured based on the electromotor force of a specific measurement cell. So we're going to be talking about the Balkan cell, which is a secondary method. And why is this a secondary method? Because it depends on a primary reference method in order to assign values. So what we're talking about here is the re-standardization of a reference material. So we use the assigned value of a reference material, which is going to be a primary reference material, in order to assign a value to our materials. So what you can see here is the Balkan cell, and you can see the load area of the cell. And what you're going to see later, or what you can see down here, is two compartments, which I'm going to show you in more detail further on. And they're going to contain both solutions, which are joined by a bridge where both solutions are going to connect. Now here in the system, we have two electrodes, which are up here, and we also have well, they're constantly bubbling hydrogen through these two steel pieces at the top. So what is the principle, or how does the cell treat it? So the equation in order to assign a value here is the one you see on the screen. Those are going to be our entry parameters. Well, what I'm going to give to the system, to the software, is this information in order for the software to calculate the pH value of the materials I'm going to be using. So that's the problem materials, basically. So now on the left, I'm going to have the sample pH, which is going to be used for this test. And then I'm also going to have two types of entries. So we're going to have the assigned value for the primary reference material. So this cell depends strictly on being able to it's going to depend on a previous pH value. So now here we're always going to be using a primary reference material where the value is going to be assigned by NIST, because we always work with the NIST. So this is a fixed entry for the system. And here we're going to have the basis constant and the Faraday constant. And up here, we also have two other entries, which are going to be the potential difference, which are going to be generated between both compartments. Because despite the fact that the instructions for the test are that both solutions have to be similar, the reality of the fact is that they're not going to be identical. So there's going to be a potential difference because the system is going to be permanently monitoring and measuring. And also, as you can see here, this equation depends on the temperature. So another entry parameter is going to be the temperature, which the system is going to be permanently measuring. So now here I've highlighted the data which the system is going to be measuring, the temperature and the potential difference of the solutions. So now here you can see the bottom part in a more clear manner. And this is the bottom part of the Balkan cell. These are the two compartments which are well, in this liquid with the chiller and which are being measured. And this is a control temperature for the solution, and that's what's desirable. And there are certain requirements that are complied here. So now in the left compartment, you can see the standard sample. And what I didn't mention before is that what I'm proposing here is a redox system, a classic redox system. So, for example, and this is going to be different to other types of cells because this doesn't generate energy, it just consumes energy. And so basically what I have on the left is a standard sample, and it's going to be the NIST sample, what I'm going to have here, where I'm going to be aware of what the assigned value is going to be. And so what's going to happen here is that there's going to be a reduction of the hydrogen electrode. So the hydrogen here is going to be reduced in order to create hydrogen. Now, this on the right is going to be a very similar solution to the one on the left. And here I'm going to want to assign the value. And here we're going to have oxidation. So it's going to be a contrary reaction because there's going to be oxidation. It's going to create 2 million oxygen plus 2 electrons. So these two solutions, which they're going to be connecting. And well, this here is going to allow for the passage of electrons. So here we're going to have an oxidation, and it's also releasing electrons, and these are transported and they travel through this bridge in order to allow for the hydrogen in the solution to be reduced in order to be reduced. So below you have a formula on how the redox formula is written. So this is extremely important. So this is an electrochemical reaction, and in other types of tests, you might have a rupture, you might have certain signals where you're measuring and they abruptly end, or you might have a change in color. However, that's not the case here. Here, you're going to have an electrochemical balance, which isn't immediate, specifically because of the volume. It's more or less 80 milliliters in each side. This might take an hour to 5 or 6 hours. So what I need here is a software which is permanently measuring this throughout the whole reaction. So now balance is extremely, sometimes it's theoretical. So what I establish conditions. So I say, okay, after a certain period of time, for example, here it's going to be 30 minutes, the potential difference when the balance is found should not be superior to a certain level. And this is something I'm going to show you next. So the hydrogen is bubbling here. So as I was saying before, it's extremely important to take into account with the software that I'm going to have to establish the stability criterion and also the time of the test and certain other aspects that I'm going to have to take into account between both compartments. So how is the software going to take into consideration all of this information? First of all, I'm going to have the equation for the Balkan cell, which is what I showed you right at the beginning. So it's going to consider all three entries, the pH value of the pattern solution, R and F, and the the data that's going to have to be taken by the multimeter and the thermometer, which are permanently going to be taken, these measurements, which are permanently going to be taken by the software, and the problem sample as well, which is going to be measured by the software. So this is a sample of the software. There are 3 tabs here, and the software has 2 modalities in addition to that. So there's the offset, and there's the problem sample configuration as well. So first of all, I'm going to show you the offset. So that's so first of all, it's going to give you that information. So this is sample to sample. So why sample to sample? Because first of all, I'm going to include in both compartments the same sample. So I'm going to let it, so I'm going to turn everything off. I'm going to put it back on. So in order to see whether there might be a slight difference between both compartments, or whether there is a difference between the electrode disposition between both the electrodes, which might have, well, there might be a small difference between both sides, or it could be that both compartments might not be exactly the same in terms of behavior. So I'm just going to want to reflect that in the final results. And that's by doing what I'm about to do right now. So the software, what that's going to allow me is to carry out this configuration. And then what I'm going to try to enter here is the correction of the thermometer, because I'm having a look at the temperature live at the moment. And I'm also going to correct the multimeter. And at the same time, this sector down here was what I was looking at before, the electrochemical balance. So during 30 minutes, we're going to have a look at the potential difference between both compartments. And we want to make sure that this isn't higher than 10 microvolts. So the software is going to allow for flexibility when we invert corrections, because, for example, from one year to the next, when I calibrate the instruments, so they might not be exactly the same. And if I were to want to carry out a testing interval, for example, the requirement, a balance requirement, which is going to be more or less strict, that's something I can do as well. And it's the same thing here with a potential difference. If I were to want to make it more or less strict, I can also change that. And down here with the reading period, well, here it says that the software is going to be taking measurements every minute for the multimeter and for the thermometer. Another condition I'm going to include here is that since, well, it's not going to be higher than 50 microvolts, because this is going to give me an idea of whether I rinsed out the cell correctly or incorrectly. And it's also going to give me an idea of how the electrodes are working, because, well, the electrodes are platinum wires, which are deposited with a small layer of platinum and palladium, which are degraded as time goes by, or just because they've had a contact with something else, they can become degraded or fall off. So when the system is measuring whether there are any modifications in the surface of the electrode, the well, just establishing these configurations can help me determine whether I'm using the right measurements for carrying out the test. So when I establish what the measurements are going to be, I might realize that I won't be able to move forward with the test, because I might realize that it's not possible to see it, but the software will be able to identify it. So as I mentioned, I might realize that I won't be able to do it, but I will also realize that the human being won't be able to take readings or to do readings every 1 minute, for example. So when I connected, in this case, the equipment and started the test, and I when I connect this and when I start taking tests, I'll see all of this, what I can see here. So for example, at the bottom, I'll be able to see the temperature and the results. So what does this allow me to do? It allows me to predict that this might be something that will eventually be easy. But for example, when I'm carrying out tests for 1 to 5 hours, to be able to predict behavior will allow me to carry out tasks in a parallel manner and not depend on this strictly. And it will also allow me to have a look at the behavior of the temperature, which is essential in my opinion. And it will also allow me to determine whether I need to modify any of the settings. And here, for example, since it does readings every minute, I mean, I wasn't going to show you what it was doing all the time, but you can see here that after 1-2 minutes, it begins issuing graphs, and it shows me the maximum and minimum readings, the potential I want to reach, and the temperature. So at the end, what's going to happen here, this test is about to finish because I had said that the potential difference had to be below 10, the maximum had to be below 10, and that the average had to be below 50 microvolts. So these two were limit tied added to the configuration. So it's active at this moment. But once, as you'll see, when it finishes, so here it finishes and it shows it's finished and the requirements were complied with. But if there are any requirements that are not complied with, the test is not finished. So for example, if the potential difference is 60, the test does not finish. That's the reason why I click or unclick these requirements. At the same time, as you can see here, these are the last this is the last information or the last data obtained, and you can have a look at all of its behavior. And the same thing with the temperature. So you can have a look at the temperature as time goes by. And when I add a solution, I can carry out tests at the 25-degree temperature. So I can add the information with the so what it does is that the temperature increases, for example, but I want the temperature to be stable sometimes. But so that's why it's important to have a look at the behavior, because if the temperature is increasing or is stable and I need to modify it, that's all important to have a look at. Another of the configurations I was talking about is, well, actually, before I go to that, I think it's important to have a look at the data collection. So once I finish the test, I'm going to want to have a look at the raw data, because with that, I'm going to continue processing and calculating the pH levels. So here I took the raw data, which coincide with what the software is showing me. So in the next presentation, I'm going to show you the configuration of the sample, which is very similar. So this is going to be a sample pattern, and it's going to have the same format. But what is this going to allow me to do? It's going to open an additional field in order to introduce the sample value, because I was saying we depend on a primary material in order to assign the value. So this is a fixed entry. We still have the R and F constants, which are constants. However, they continue to be studied, and it could be that throughout time, some of these numbers might change. And in fact, in 2018, that was the last time when we put them in, but they had to be modified because these fields are open, and it's desirable that they're open. Because if I include these, I'm going to ask Pablo to modify or change this, because that's the reason why they're left open, and I'll be able to modify them. But also we have the potential difference due to the target, which is what I calculated. But this field is open because all the offsets included are going to be the same. So this field is going to allow me to modify them and include the offset I need. And the temperature correction fields and the ones for multimeters continue to be fixed because that's going to include the same configuration. And this is all going to be the same. So this is going to be a bit different because I'm going to unclick the potential because I'm not going to say it's going to have a potential difference between both solutions because with the offset, I said that both compartments had the same solution, but here I'm already analyzing the sample. So it's not necessarily going to have a sample pattern with a problem sample, which are going to have a potential difference that's going to be below 50 because this sometimes happens and sometimes doesn't happen. It depends on how I produce the batch. So it's always done with, by getting as close as possible to the pattern value, but there are always differences here, which I'm going to want to measure in order to assign a value. And at the same time, this allows me to save the configuration as a predetermined configuration so that when I open the software again, I have the same configuration without having to change permanently change the data whenever I'm going to carry out a new test. So that's what I was saying a moment ago. So we change the information for the pattern in this case. And in this case, it was a pattern sample of about 9 with 2. So I'm going to enter the information of the assigned value, which is what I'm showing here. So what I have here is the offset value, which I just calculated. So I'm going to add 6.22. And the difference of the potential difference here is the balance I'm going to assign, which is going to be the same as for the offset, but the maximum difference has to be higher than 10 microvolts with a time interval of 30 minutes. And that's going to be the same. So that's the electrochemical balance I'm imposing. So I'm going to connect the equipment and I'm going to start the test automatically. When I'm working with a prior test, it's going to leave the previous graph. It's going to delete the data on the right. And then when I begin the reading, this gets deleted and it begins creating the new chart. So I'm going to use the same modality as for the offset. So I click on XLS and what it's going to do is that it's going to remove the data in order to process it. So now I will give the floor to Pablo.
Pablo, te han dejado 2 minutos para...
Pablo, you have 2 minutes left.
Me alcanza con 2 minutos, no se preocupe.
2 minutes is enough. Don't worry. I just wanted to say a few words on a few technical aspects regarding the software. You're muted, Pablo.
Sí, ahora te escuchamos.
We can hear you now. So there is a new version which is being created because there was a compatibility problem with the operational systems. Communication is with the GPIB card. So it's not a port, it's a card which has its own language, which is called 488. So in order to work with this, it was necessary to create a component. So we developed it ourselves in order to manage the 488 of the card and be able to operate adequately. So in order to operate with LabVIEW, basically that's the language we use by nature for this type of equipment. And the equipment is there, you can see it. The main challenge we've had has been with the multimeter because I mean, with most of the equipment we use with the communications protocol works a bit differently, but this equipment saves the data in a memory buffer, and most of the data wasn't being saved completely, and this generates data that does not comply with all the requirements. So if you're seeking stability and there's data that falls far from that, then it creates a few problems. So we needed to create something that would lead to a more stable process. So we had to previously validate the data we were going to be using according to the trends in other data. So I just wanted to show you that apart from the configuration or setup window that Victoria showed you, we also have other information we can have a look at. And normally, well, in this example, we have all numbers, we're following a trend, but we have one that was slightly different with a different sign that led to a peak. So this led to the generation of a new time, but really we'd already found what the problem was here. So just wanted to show you that. So thank you. Well, thank you, Victoria and Pablo, for your presentation on measurement methods and automation.
Estamos con un poco de problemas de tiempo.
So we're a bit tight on time, so we're going to try to answer a few questions. We're not going to be able to answer all questions. So first of all, I would like to ask Lars 3 questions. One is from Ryan Henshaw.
And then the next question is,
So
does the Calibration Scout give the customer an estimated time for submission of the instrument? If the item has a code to the scan,
if
pose a confidentiality issue if someone other than the customer can scan and see the certificate as well. And related to that, the question of Cyranox, does the customer get an idea of how long the calibration will take in real time, especially if the equipment are in the system already? And from Diego Copa, are you planning to use DCC? You already said something on that, but can you elaborate a bit more what you are planning and how you're involved in that development? So Lars, please.
Yes, thank you. So I will answer. No, at the moment, there's no possibility to receive some information about the estimated time or or some kind of real time. We plan that not in the Calibration Scout, but it's scheduled for the software solution Trendic Hub, and we will offer that maybe in December of this year. So the second question, if the customer can scan the code, but he has it's some kind of application. He has to open his application, so he has to sign in with his customer number and his password, and then he can scan a code and receive a certificate. So it's not possible for other customer to scan or to have access to the calibration certificates of other customer. So that was the same question. Does the customer get an idea how long the calibration will take? No, not at the moment, but at the end of the year. And the last question from Diego Coppa was, are you planning to use the DCCs for your customer or for in-house calibrations? Yes, at the end for both. So we are a partner of that project. So we started working in this project with Siegfried and his team. Our idea is to use that, of course, for our standards we use in-house. And then we will also offer that for our customer. And there we are planning a project already.
Thank you very much, Lars.
Okay.
Patrick, from Juan Lugo, what is the before and after automation in terms of incomes, human resources, and time invested in calibration services? From Diego Copa, how you install a M4DT server to deal with all the instrumentation? And from Luis Manuel Peña, do you have automated mass comparators and robots from the manufacturer, or have you automated the mass comparators at NIST? And lastly, from Alan Dominguez, what uncertainty contributions should be considered in a robot-operated weight comparator? And what uncertainty contribution should be considered? These questions.
Well, thank you very much. The first talked about generally savings, and regarding income, we're not sure yet because we've only been doing it this year and we don't have a lot of data. But I should say that our income from calibrations year to year is generally dependent on our customers. Our clients in general are on their own calibration cycle. So we have several clients who are on, say, a 4-year cycle where we won't see anything from them till every 4th year, and then we see lots of business from them. So we tend to have lots of clients like that. In terms of human resources, in my talk, I think I emphasized there has been a big savings in terms of time spent in analysis. It was a very arduous process before, and now we can literally analyze data that was taken over a series of hours, maybe 13 to 20 hours, something like that. We can analyze it in just a couple of minutes. It's been a huge time savings. So that's helped us make decisions about what further data we need to take, and also has enabled us to do some other things, because as NIST employees, we have other duties in addition to calibrations that we have. Each one of us has generally some other projects to work on as well. So it's helped on the individual employees' time schedule. Let's see, what else? I guess for the amount of time spent doing any given calibration, automation has enabled us to save lots of time in some of the work down procedures that required several days of very intense weighing designs that would be done by a human being. That would take maybe several hours a day for perhaps 3 days to get all the data necessary. And in some cases, we can do all of that at night and on 2 or more machines that are operating at the same time. So this has helped a lot with mistakes generated through operator fatigue, and just being able to repeat things. If we wanted to repeat something, then we didn't have to worry about an operator having to go through maybe another 10 or 15 hours worth of labor in order to get another piece of data. So it's been a really, really big help for us. Second question regarding the M4DT server. No, we have not installed one of those. All of our instruments are connected via a docking station that goes right to an individual laptop computer. And that laptop computer is running the software that we've made from the NIST centralized server. So that's how we do it. Let's see, the next question, commercially available automated mass comparators versus doing it ourselves. Yes, all of the automated mass comparators that we use are commercially available. They were purchased from vendors. However, we did not purchase software or any add-on instrument packages that go with them, because we found them to be very limiting in terms of what type of data we wanted to see and what we wanted to do with the data, etc. So we decided to take our own route, and fortunately, for the most part, the vendor software was flexible enough to allow us to do that. Uncertainty contributions, that's a great question. Being a metrologist, you're always concerned with such things. And two things come to mind with the robots. First of all, temperature uncertainty. I don't know if you were able to appreciate the enclosed volume that each one of the robotic comparators is inside, but it's a fairly large, maybe a cubic meter or so of volume that each comparator has inside of it's plexiglass basically. And as you begin to run the comparators, the automated robotic comparator, things get warm. And we've noticed that over the course of the first 3 or 4 hours that we can notice a fairly repeatable pattern in terms of temperature increase on the order of maybe 0.2 to 0.3 degrees centigrade. And it's very difficult sometimes to know how that's affecting. It depends on each individual weight. So generally we use the first run or maybe the first 2 runs in any sequence of measurements as sort of a warm-up, and we wait until we have a steady temperature before we start looking at any data. So that's one source of uncertainty. The other is these robotic arms are very precise, and they put masses on the weighing pan in exactly the same position with exactly the same amount of force every time. And these can lead to very, very small type A uncertainties, which are not at all indicative of what a customer would use. So if a customer is using a 1 kilogram mass on a manual comparator, and he does some comparisons, then he's going to see a much larger type A or if you will, random component to his uncertainty than we would see on a robotic comparison. So that's something else that you need to figure out how to deal with. Let's see, finally, the cost of all of this. These automated comparators are very expensive. I cannot lie about that. They're several $100,000 a piece. And we have built up all of our instrumentation over a period of 15 to 20 years. And the software efforts have only been going on for probably the last 5 that we've been involved in this software integration and writing all these applications now for uniform software. So it's a large investment, but it does pay off at the end, because we're seeing now that we can run lots and lots of instruments with very few staff members that don't necessarily have to be around on site to do this. So thanks very much for your questions.
No, thank you, Patrick. And as a comment from my side, I think you increase the human interaction by this investment because you have more time for your colleagues and to discuss deep questions on metrology.
Yes, that is true. At the end of the day, you still need good people to do these things, and you need to discuss with your colleagues what they're doing. That's right.
Bueno, thank you. Como última pregunta.
The last question for Pablo was, this is from Ruben Hill. According to 17025 on software validation, has this been considered when developing the pH software? During the design stage, we validated how accurately the data was being taken. So that's when we had the problems I was talking about regarding the multimeter. Now, regarding the validation of results, as Victoria said, the software basically offers a practical framework for carrying out the tests, the time frames in order to reach the proposed conditions, the carrying out the tests without the participation of an operator. And as Victoria said, we put all the raw data in an Excel spreadsheet, and that's how we calculate whether there's uncertainty and it's necessary to carry out further processing. So in that case, it was not necessary because those results aren't used directly. Thank you, Pablo. Thank you, Lars, Patrick, Victoria, and Pablo. And I apologize for having taken so long, Herman, because these have been very interesting presentations and questions. And that's the reason why it took so long. So, Herman, now it's up to you to manage time. Thank you, Alexis, and thank you to all the panelists with this a very interesting block, because as Alexis was saying, these were very important and interesting topics, which is why we took a bit longer than planned. So as we said yesterday, we are going to ask everybody to turn on their cameras to take a group photo. And after we take that photograph, we're going to ask Marcia to let us know so that we can take a 5-minute break. So Francisco, please go ahead. So could everybody please turn on their cameras? We need to take several screenshots. So please turn on your cameras. That way we can take the screenshots as quickly as possible.
Un momento más, por favor. Vamos. Somos...
One more minute, please.
Muchas gracias, Germán. Muchas gracias a todos.
Thank you, Herman, and thank you, everybody else. Thank you, Francisco. As I was saying, we're going to take a 5-minute break, and when we come back, we will talk about digital twins. We will have 2 panelists, Hugo Gasca and Aldo Garcia, both from the National Metrology Center of Mexico, CENAM. So we'll see you back here in 5 minutes. Thank you.
Operation Group. Cordial saludo nuevamente. Regresamos con nuestro...
Welcome back. Now we're going to continue with our last block about digital twins. But before that, I'd like to remind you that in the chat, you will find a link for a survey so that you can answer this at the end of the event. And as I was saying before, we're going to start with the last block on digital twins. And here we have Francisco Flamenco, who will be the moderator. He has worked for over 7 years as information director in CENAM. He has a master's degree in computer sciences and has participated for the last 2 years as an expert supporting the working group on digital SAE of CAPM. So welcome, Francisco Flamenco. Thank you for the introduction. Welcome to the final block with the topic digital twins. We'd like to remind you that you can ask questions in the chat. And at the end of this block of presentations, then your questions will be answered, both for the social networks as well as this platform. Remember to write down the name that your question is addressed to. Dr. Gasca will be speaking about implementation of a scientific metrology cloud kernel as a byproduct of the digital twins. Dr. Gasca is the current chair of metrology for digital transformation of SIM, as well as collaborating with an active member of the research network of Mexican researchers, and working on a SIM working group and chair of the IMECO CG group on digital transformation. He has a PhD in mathematics and statistics and since 2013 started collaborating with the National Metrology Center as a management coordinator and in relation to national standards and as a specialist consultant on applied probability and statistics. So go ahead. Thank you for the introduction, Francisco. Good afternoon, everyone. I'm going to share my screen. And please let me know when you can see it. We can see it. Thank you very much. So we're going to speak about this process or this progress that we've achieved in CENAM in recent years. And I'm going to explain it very briefly. It's just going to be an overview, a summary. I won't be able to delve into the details because of the time limitations, but we will ask questions at the end. So the content, I've structured it like this. We're going to speak, because it's always good if there are new colleagues, industrial colleagues, who are hearing about these topics for the first time. It's important to go into basics, definitions, to distinguish between the digital models, shadows, and twins. Then we're going to speak about general requirements that need to be satisfied for this technology. The proposal is the core, the kernel, and some additional requirements that go beyond the general current requirements that are documented. Regarding the digital twins, we can understand, first of all, they have several components. They have one component that is a data structure, the attributes, the fields that define the properties of these virtual devices, these objects that were mentioned earlier. And you will hear some things that overlap too. And also in relation to ideas that Siegfried shared yesterday, and also that were shared today, also by Abbott and by Lex. And a second component of virtual devices is their behavior and their functional behavior related to processing of attributes and the interpretation of the data. And finally, a component of interfaces, how we communicate with these objects, with these things, these devices. And there are several layers of interaction here. We have one part related to response, and we investigate what the responses are to the stimuli of these objects, but also control commands for controlling the configuration and the general properties of this object. And furthermore, there might be another layer of programming. It's not just a question of requesting a value or saying change the frequency of a sampling in this way to a certain frequency, a certain time, but it's also possible to have a layer, a programming layer to communicate with these types of objects. So that's in relation to the structure of a virtual device or a programmable object. We can also understand here, and I'd like to clarify something here regarding the different levels of abstraction or coverage. We can start on the left with the model with the 3 parts that I mentioned related to the data structure, the behavior, and the interface. But also it's important to be able to control the virtual devices. That would be one model. At this level, we can start to have simulations. We can't just have simulations with data or just with algorithms. We need the 3 sides to be able to control these devices. So we need a kind of environment where we can locate these digital models. In the past, over the last 2 years, this term of digital twins, in accordance with our experience in the meteorological environment, would appear to be just a simulation, but we're changing its name. That's what people thought, but that's not the case. This is something that you can carry out using models. Also, apart from models, we have the shadows. The digital shadows include the whole model plus the capacity of automating data acquisition. So this is something continuous. This additional capacity becomes a shadow of the physical object. The next level, further to the right, is this shadow, but also control over the physical twin. So this block that Dr. Abbott presented related to automation, so we can automate this activity, and that's normally a technician that needs to place the masses in the corporators, but now we have a robot, and now we have control over the physical object, and we do this through a command. So this becomes a digital twin. This is just to clarify somewhat the range of different approaches or the coverage of the activity. As we move from the model to the digital twins, then we reduce the interaction and the need for control by a human being of this situation because it's an automated process. Now here, the precedents from 2016 to the present, we started with this task a little earlier. We started by modeling standard masses and then block gauge. And we have shadows for acquiring data. And what I wanted to explain in this slide basically is that the data structure that's involved, obviously there are a lot of indications and different interpretations by different instruments, but the final result that we obtain from this calibration or measurement is a specific value, a scalar, it's a point, and this is related to uncertainty. So something that we started to see was that it was a specific value, but it's necessary to have a temporary extrapolation over time. And then we're going to speak a little bit later about this in order to clarify the idea. And also sometimes we use digital thermometers, and this thermometer again measures a point in time in accordance with the control, and we don't make comparisons. Maybe this example isn't completely up to date, but the quantity of the interpolation, here it says no, and we need the temporal extrapolation too. The third example is an analytical balance. It's a continuous response to the stimulus. if you have a 2 milligram mass compared to 20 milligrams, 200 milligrams, any intermediate value will give us a response, both for the value and also for uncertainty. And here we start to look at the possibility of controlling the response of the instrument, of the device. And it could be a shadow, a digital shadow, and a digital twin. And here we need interpolation between the values. We calibrate it for certain specific points, and then we present a different value to the one that we have calibrated. We need an interpolation technique to assign a value to this new stimulus for the response that we have to the new stimulus. And then here also we need the temporal extrapolation. Why do we need this? For example, if we have an analytical balance on a certain date, and as Patrick was saying, if we have a date, and then we can use it in the future. So we have information for the past, and normally we assume under certain criteria that have been reasoned and justified that this won't change. So in the immediate future, over upcoming months or years, the response will be the same. In fact, we're always extrapolating for the future. Another example of a device are microphones, reference microphones. These have a response which is more complex. They have an extension or a breadth and a phase. And the point is that the response is continuous. It has a continuous two-dimension region. It's flat, not curved. Again, we do need quantity interpolation for the nominal value where it was calibrated, and temporal extrapolation for unknown future values. And when we use this after having calibrated the device, again, we're using information from the past to infer a future response. In reality, it's in the present, but the information about the calibration is in the future. So we are applying extrapolation techniques under the assumption that it hasn't changed and that this value continues to be valid, or this response continues to be valid. So in this task, we started, as many laboratories have done, with calculation sheets. And as we've progressed, we started to use other languages, such as MyView, Python, and Airy. Then there was a need for reusability. And something that happened with the spreadsheets was that somebody would develop them, then apply them to a certain area, a certain laboratory, see the benefit, and then export them to a different magnitude. But the reality is that changes start to occur, and we could have an infinite number of versions of the same, and to each one we could inject errors, so we need to test them. This is a huge effort to test so many variations and so many versions. So this is one aspect. Another aspect would be the use of these models or shadows or twins. We need an environmental environment, shadow environments, so that we can interact with them. to be able to investigate, to be able to change the stimulus, or to acquire data from an experiment, a measurement, and then investigate and process this information. So this has been done also in Senam in a laboratory. So we have a whole range of these environments for controlling the experiments in each laboratory.
So this need to reuse this level of knowledge takes us to the right environment for the digital twin manager, which is an integrated environment. And this leads to us analyzing how we're going to interact with these models or twins. And so currently, what we believe to be the best options are XML or JSON as the right languages for exchanging information, and QR codes for identifying what we're talking about, what tools or devices. And in addition to that, instead of using tables or coded files and binary code, we structure that information in order to use information processing for this data structure in a homogeneous manner. So due to the need for reutilization, there's a need to integrate an environment so as to manage these objects and to organize this data, which is what we were talking about, or what Dr. Abbott was talking about. So now there's something we're going to talk about further on, but there are several options for exchanging information. The DCC focuses on the implementation of XML. And that's for good reason too. So now there's a more specific example here. It's more of a conceptual example, but now it's important to explain because it explains the situation prior to digital transformation. So we have human intervention down here at the left in order to put this weight on these scales in order to then read these data using a middleware. And in general terms, what we do is we take this information, sometimes by hand. And so there's human intervention, basically. So in general terms, this data is put into spreadsheets, and using software, we generate a report. So with software, we generate a report, we put this into a PDF and then send it to the customer who must read the certificate, interpret this calibration certificate, and then through a middleware software uses it with new measurements, which they also need to use with a device measurement, and they use reduced models in order to correct bias and calculate the uncertainty of their measurement when using information that comes from a digital certificate. So there is a chain here that continues and goes on to their users. So this is a common scenario prior to digital transformation or automation. So now how does this work here? We have human intervention with the equipment if it's not automated. And now the part regarding data acquisition, for example, when we have a shadow, which would no longer be a model, but a shadow that acquires data, and this carries out the processing stage. So we acquire this information here, which would involve a digital certificate, which could be done on XML with a QR code to trace it. And there would be another layer here in a virtual space that would interpret this information through a machine, and it would be captured in a calibration repository, which would be associated to this twin or digital shadow. And you have here the algorithms that could interact here with this virtual object through a manager or a programming environment. And what this would allow us to do in those cases where we're moving forward, and because I mean we have many digital twins, so what we do is that we'd gain control through these devices. But what we're achieving here is that we're being able to analyze this or what happens with this virtual environment. So it's allowing us to learn and or gain insight in order to improve this physical device. So that's one of the main benefits of these technologies. So basically, this is the same thing. However, here I'm talking about virtual spaces on both sides of the process. So this is a completely virtual environment. And the question here, or the proposal here is for the DCC to be a well, to give us a view of the scientific metrological database, and what we can obtain from this digital certificate is this calibration repository. So the calibration repository would be a partial view of the digital certificate, which in turn is a partial view of this database here. So in order to carry out simulations, to investigate and analyze or learn or study with more detail, it would be convenient to develop the digital twin or the algorithms using the scientific database, and not to develop this information based on the digital certificates, because it would the information would be too summarized and we'd lose too many details. Doctor, you have 2 minutes. Sorry. Thank you. So since we're talking about behavior, what I was referring to is the tool as something that we put into a digital certificate, a calibration digital certificate. So for example, a correction, we have to carry out to certain points when we're calibrating, but with a continuous response with certain level of uncertainty in the model. And there's also the uncertainty in each of these points where the measurements were carried out. So for example, I don't know if you can see it here, but there's a gray line, a certainty bar, which you can see on the right, which is a point for the level of uncertainty for the measured value. So you can measure the error and the uncertainty. So this is something that's carried out with curve adjustment techniques and uncertainty propagation. And these are all classical techniques. So this is something that you can measure. So these are all normal techniques. And so if you consider the uncertainty, we're talking about this region here. So these are all just normal classic techniques. So we can use more advanced techniques in order to take into account historical information or data regarding a group of objects which are all similar. So we can use here in this chart the information provided regarding a device that had 24 sensors. And we can have a look at this. Well, it's a bit complicated, but sometimes we might have to use complexity reduction techniques within the data space, and we might have to carry out a comparison based on the areas with the most information. And in this case, this technique allowed us to carry out a more accurate analysis. So the green points provide us information on these devices, and the red points provide us information on the flaws of the device, and the gray areas give us general information, and blue gives us the evolution of two of the instruments measured. And clearly here we can see, well, not that clearly, but maybe the red horizontal line gives us the reference point where it's necessary to take corrective actions. So, I mean, before that, it was an operation, a normal operation, but and there was no risk, but maybe this would be the case of measurement instruments that fail, that need fixing. But it could also refer to other types of situations where preventive measures have to be implemented, such as a pacemaker that needs to be replaced after a certain period of time due to use. So, for example, devices within an aircraft. So these are many uses that these techniques can be used for. So, for example, we can carry out predictive maintenance, big data, complexity reduction, artificial intelligence, data clustering, for example. So fleet learning as well. Now, requirements, what are we talking about here? We have BIPM and CIPM FAIR principles. We also have the units, international units digital system, and this is all extremely important regarding the DCC. So this is something to take into consideration because it involves other players as well, which have proposed this. We also have the VIM, GUM, and BIPM, and there are other general requirements based on the level of magnitude being measured. And we have ISO or ISO and others. So in general terms, this is the scheme used currently at SINAM. This is based on the current database, and there are certain information entities which cover the 17025 requirements, such as the client's data, the calibration laboratory, measurement results. So that you can see in the blue box, and there are things that are covered by the DCC, as we saw before. So that's a partial view of the problem. And so what 17025, so we have 17025 plus the International Digital Unit System. Then we have the VIM, which covers other aspects, but the VIM doesn't really refer to the client. It doesn't talk about the calibration laboratory either. The VIM talks about the measurement problem, and it overlaps with the measurement result as well, but it talks about measurement system, devices, measuring, other terms as well. And the GUM doesn't talk about this all that much, really. It might refer to it slightly, but it mainly focuses about the measurement, the measurand, the measurement function, indication input quantity, and input quantity. So as you can see, we have many requirements that have to be complied with, and many of those overlap. So we have to link them together, because as people working in metrology, we have to comply with many of these requirements, and the database must take this into consideration. So, Hugo, we are a bit tight on time. Thank you. So I've only got 2 more slides left. So this slide is from a RAMI publication, which is a reference document for Industrial Model 4.0. And as we can see, there is a physical layer. So this is the shell that covers this physical thing. And we have several layers. There's a communication layer, an information layer, a functional layer, and a business layer. And these are all above the integration and asset layer. So I would say that in the business layer, we also have the legal layer. And here there's something which can be looked at from two perspectives. So we have how the management or administration shell can be looked at from another perspective. It can be looked at from the perspective where it can be looked at as something that will cover the physical twin and the digital twin, or where the digital twin will be covered by the physical twin. So it's something which is desirable, where we get somewhere where a physical object will be replaced by its digital twin without anything else changing. And we have another reference. This is something that Senam isn't inventing. We have well, a proposal of new requirements, and everything I've spoken about is taken into consideration the technology we've been talking about. So there are measurement devices with the Internet of Things. So now this is something that we've spoken about in other conversations, with the integrity and authenticity being taken into account. So how do we guarantee this? And how do we guarantee that the cloud connections will be able to have access to what's being measured through a specific sensor, and where this information will be private? So there's an additional layer here, how to verify integrity and authenticity of these access schemes and of this information, and with those who are taking this into consideration, but that's the users of this information. So as you can see, the problem is broad, and there are multiple faces that need to be taken into consideration, many stakeholders, many interest groups with various requirements. Thank you very much. Well, no, thank you for your excellent presentation. It's extremely helpful, and I think it helps everybody else to be aware of what we're doing. So the questions are going to be asked at the end of this block. So I would like to remind everybody that if there are any questions, please include them in the chat. And now I would like to introduce Aldo Garcia, who is going to be talking about first steps towards the development of a digital twin. Aldo Garcia works at the National Metrology Center, SENAM, and he is an expert in the acoustics area in SENAM. And apart from calibration, apart from being an expert in calibration, he is an expert in instruments and also in transductors. So he also has knowledge in measurement laboratory standards and uncertainty levels. He works on improvement or constant improvement in the implementation of agile models. He's also the leader of one of the working groups on digital transformation under the name of Streamlined Project. So welcome, and go ahead, Aldo. Thank you, Francisco. Thank you, Hugo, for your presentation. It was a very good presentation.
This presentation in English. I hope there is no problem with that. Thank you all for your assistance here in this conference day. I'm going to talk about the first steps towards the development of a digital twin. And as you know, by the previous presentation, Hugo gave us the first steps and the first knowledge about how we can implement a digital twin. And I'm going to share with you how we can implement the digital component twin in a different strategy as well. And you know that all NMIs wants to develop everything. They want to take control of every process and measure everything. But we need to apply in these first stages some strategies that gave us the opportunity to be faster with the industrial necessities. So in that order, I'm going to present this information to you. During the presentation, we will be showing an introduction, definition, and examples of digital twins and the types of digital twins. As you know, thank you for the presentation of Hugo. The digital twin is a virtual representation employed to understand and foretell the behavior of its physical equivalent. So the digital twin term was designated to a ubiquitous strategy, owing the vast array of its applications in various fields. Essentially means that it is a virtual representation employed to understand and foretell the behavior of its physical equivalent. In simpler terms, digital twin is a digital replica of a physical product in all its aspects. The later half of the sentence implies that the digital twin observes the entire life cycle of its physical counterpart through sensors and store it in the form of data that is thereafter used to simulate the behavior and even optimize some actions in the behavior of it required. So this concept was first introduced at the presentation held at the University of Michigan in the year of 2002, but the concept was named as a digital twin by John Vickers of NASA in 2010 roadmap report. This technology was already being employed by NASA, the largest space organization in these projects, and NASA used the basic replication ideas during this period as a development strategy for many of its space programs. NASA created duplicates of the system in space to study their behavior on the ground. So we can understand that it's important to have this knowledge and to develop the necessary tools in order to achieve the progress in metrology and digital twins. Okay, so I'm going to speak very fast because we don't have so much time. I put here some examples for right now for this COVID-19 issue. There are some examples of the digital twins can help to improve and to better the life of everyone. So I'm going to explain very fast these two examples. This first example is digital twin modeling for vaccine manufacturing. Pharmaceutical companies have a bioreactor plant, which is a system that supports a biologically similar environment to examine reactions between chemical and biological substances. Every reaction that takes place between the ingredients in a bioreactor must be monitored, which involves a significant manual effort. The digital twin can aid the monitoring process with the initial conditions of a bioreactor that are duplicated and fed as a data to a digital twin model. Any change in the digital twin data value indicates a reaction has taken place in the original bioreactor. This reaction is immediately recorded, stored, and in a database, and a notification is sent to a pharmaceutical engineer who has a mobile application associated with this digital twin. This application takes the help of machine learning techniques to foretell the value of import process parameters and even makes decisions to improve the performance of the process that is in progress. Researchers can use this data to determine the compatibility of a vaccine, and this depicts how digital twin modeling can be employed in the pharmaceutical industry to aid vaccine manufacturing research. I'm going to jump to the next slide. Sorry, but this other example is very interesting because they replicate along and by a 3D model, then they can simulate how the blood and the oxygen flows in the body. They can simulate this information with artificial intelligence and have predict ventilation requirements for a system to assist a person that has some issue. I'm going to go to the next slide. So here are the potential of the digital twins. The 3D representation, the measured features of physical object can be mapped on a 3D model. The visualization, a graphical representation of the product can be portrayed either on a physical device or in a system. The data model is simulated for visualization, connection, and analytics. Model synchronization. The digital twin model is aligned with some real-world parameters. Simulation. the object is viewed in a simulated environment to record its behavior, document management, all the information regarding the product life cycle management is maintained for future reference. The model is the performance and status of a physical device and characterized in digital manner. And the next and final thing is connected analytics, and this about the measure. Okay. There are some different classes of digital twin. Digital twin works in bottom-up approach, which provides more knowledgeable multiple types of information with each and every layer. The 4 types of an emerging hierarchy of digital twins are depicted in the this picture. So the term component in component twinning represents that they are made twin of a single component in the entire system. They have the significant impact on the performance of the asset to which it belongs. The physical representation of individual components allow the engineers to recognize the physical, electrical, and mechanical characteristics of a component. My example that you are going to see later is this kind of digital twin. It's a component that involves the digital twin. Okay, there is the asset that is the next higher level of digital twins that can be defined as a collection of component twin, or it can be gathered to the information from component twin. An engine is a best known example of asset twin. To give a better outcomes, asset twinning make use of individual products to work together as an entire asset. The next one is the system. Okay, the next higher level of digital twinning arises after asset twin is system thinking that permits the engineers to run and operate the entire fleets or of disparate products to work together to achieve the best outcomes. They show the visibility across a collection of equipment. System twin has the capable of analyzing the working of individual assets together. They can be applied for various types of applications. System twinning is also known as unit twinning. Let us consider the car factory as an example of system twinning. And the last one is the process. The process twinning is a higher level twinning that represents a whole production process and provides insight into the collaboration of all other systems. The far most important factor to be considered here is timing. So I'm going to go to the next slide. Right now we are going to talk about the example that we implement in collaboration with some collaborators or clients that request us some solutions, engineering solutions with measurement solutions. The scope of EPICs that were originally defined were intended to develop a system that integrates elements of Industry 4.0 and Metrology 4.0. But looking towards the trends within the industry, digital twins will be required to optimize the process, and all the elements developed can be used by the company or client to develop a GIM component. So here we can see the process. We develop a high resolution vibration analysis algorithm system using accelerometers. Then we develop an algorithm to upload measure data to digital data cloud by XML and metadata. Then we apply the Industry 4.0 and Metrology 4.0 knowledge to the solution. And in the future digital component twinning in collaboration with the client will be performed later. We apply a methodology. This is important. We need to give the solution with a very well-known methodology. So the methodological projects are focused in the development of systems that adapts to the customer needs. In this case, a vibration analysis system test. The cell was developed to measure the health of the mechanism inside of tractor differential in a production line. And we follow this. First, we know the design. Then we define the know-how to implement this measurement to this machine. Then we understood the technology, metrology, know-how. Then we apply evaluation. Then we apply the communication between machines. We establish the fundamentals of the database, and then we propose with the software of the client a digital component twinning. So we have important aspects of the project. This is a very important thing that we need to perform. Is the creation of a line design and manufacture of equipment for functional testing of automotive transmissions. One of the most fruitful avenues for innovation methodology is when integrating measurement technology into direct industrial application equipment. Online functional and dynamic measurement is fundamental to smart manufacturing systems like Industry 4.0 and digital twins. The measurement of functional parameters of manufacturer system poses complex challenge due to the combination of variables involved. This article shows a successful example of system integration for measurement of this type achieved by the institutional collaboration with the stakeholders. And it is hoped that examples such as this one will open the way for the development of an integration and instrumentation industry at SIM. So we apply this structure with our basic control process. We have considered all the functional requirements of the design, set in a design parameters that allow us to have the necessary data for the control system. On the other hand, we have the inputs or variables of the measurement system that will be taken into the machine to run the necessary raw routines to achieve the desired objective. Through sensors, we obtain the necessary information for the control stage, where they are compared with the functional requirements and the feedback to our machine, and determine whether these requirements have been met and ultimately have a quality product and reduce cost. So we need to understand the needs of the client. The client says that manufacturers and assembles powertrain differential mechanism for tractors. All powertrain components combine material, strength, hardness, weight, dimensional length, diameters, complex shapes, and functional requirements. Among the functional requirements of the differential gearbox are pinion and gear interaction, misalignment, bearings, backlash, torque, or residual friction torque. The customer requires at the end of the assembly line a workstation that allows to measure the previous parameters and others coming from vibrations inside the mechanism at 100% of its production in dynamic way, and to determine if the differential passes or does not pass according to a study made to the differential model. And the last one was machine-to-machine communication. Okay, so the part of design, we need to know and then understand the needs, create a design, create a model, and test and evaluation for known and then understand the needs. We want to increase quality production, reduce assembly defects, and the noise caused by them in a pass or fail system. Create a design, research about tractor differential mechanism, define functional requirements and the designer parameters. Create a model. We develop a test bench to generate measurement knowledge, test and evaluation in iterative experience process to improve measurement system and the technology transfer. So in the part of creating a design, we need to understand how it works, the mechanism, the number of teeth, the driving pinion mounting distance, pinion offset below center line, ring gearing mounting distance, gear nominal backlash, assemble backlash reference, tooth flanked, all that elements that give us information, and we can expect some kind of signals through the accelerometer measurements. Okay, so then you are seeing here that our designers in collaboration with another company, we work together and set the first parameters to know how we can apply the metrological assurance, and some functional requirements to the designers to apply the best practices of accelerometer measurements in the machine. So they get our information and they put it in the designs. So we can see two pictures here. This is the design that they develop, and then the implementation, the manufacturer test bench that we have here in Senam to create and to develop the knowledge to be implemented in the industry. Then I'm going to put this video, and this is our test bench. Here we develop the know-how to bring to the solution at the end of the line. So here we can understand about speed rate, rotation, accelerometer points at the structure, what we expect about the excitation and how the mechanism generate vibration, how to mount the accelerometers, and how we are going to expect the isolation of the ground to the machine. So then we transfer this knowledge to the final stage at the industry. As you know, here I'm just telling you how we perform the different steps, and later we are going to explain how we apply the digital twin. So here in the industry, we give them we transfer them the knowledge about how measure, and all these functional requirements are plasmed here in this final product that is the final machine. So I'm going to reproduce sorry, this video. Yeah, there is. So you can see here that all the knowledge that we get from our test bench, we apply it here in the industry. And all the measurements we check that were performed in the proper manner, the proper way. And to know if there is another thing that cannot be expected during the metrology assurance, with the position of the accelerometers, the signals in the data acquisition system, and so on. Okay, so the system, here we are going to talk about the machine-to-machine communication. We develop a software in LabVIEW with my partner Manuel Alejandro González Duran. We develop a software that we use to measure the accelerometers. We apply some knowledge about RMS analysis, in time analysis signal and factor crest of the signal to determine if these models pass or not pass through a very exponent analysis during a lot of models of different kind of differentials. More or less, we test 100 or more different models of differentials, and we get information about the vibration amount of the amount of vibration of every model. We characterize the vibration in time of each model. So we have that database, and we store it in the computer bot. One requirement was to communicate this information to the software of the client. The software of the client has artificial intelligence to prepare and to know with our information, with our suggestions, and the setup of different points of comparison to know this level of vibration is correct, but if you pass this amount of vibration, you are not correct. So this software can interpret this criteria and then send back the information to the machine to stop the operation and indicate
2 minutes, please.
Yeah, thank you. And indicate to the operator that this differential must have to be checked. So this is the first approach. As here is a picture of the software. We record here the vibration and form or of the different accelerometers inside of the machine. And we work to collect data obtained of this test of the differential to establish new limits. This is our work. We prepare a model. Senan prepare a model to feed the software that the client use in order to have the criteria to accept or not accept the models when the differentials were measured in the machine. So then we prepare how we communicate with the software's clients. We use XML. They gave us the labels, all the information, the structure of the XML format to communicate with their systems. And only we just added to the final loop of our program that share the results as pass or not pass, the vibration analysis, the value of the results, and the number of or the number and name of the model that was tested in that machine. So in real terms, we apply the digital twin component because we have the real machine that are measuring with real accelerometers. We pass through the information of the raw data, XML data, the certificate, calibration certificate of the accelerometer, the certificate calibration of the data acquisition to the virtual client software. And they gave us some info about the calculated new trends and the process, some adjustments to rework with the differentials and so on. This is a diagram that represents how we implement this. This is more or less the information that I already talked with you. All the communication through the machines were on XML and with the software of the client. In this way, we increase the production quality and we reduce the cost of the production. So we want to say that we want to add agile model to develop projects, Mesura and Agile. We want to include DCC to digital traceability and digital twin actualization. We want to implement our own artificial intelligence algorithms for focus on metrology, implement DSPs for real-time process improvement. We want to develop better toolkits of XML metadata and remote verification for accelerometers. And for last, here is a video of colleagues in, I don't know if it's in Japan or Korea, but they are showing us a very good video of how we can know if it is a digital twin. So thank you very much. If you have some comments, please, I am at your orders. Thank you all.
Al contrario, muchas gracias, ingeniero Aldo, por tan brillante y tan descriptiva.
Thank you for your brilliant presentation. It was very descriptive. So now let's go on with questions and answers. We have a couple, actually we've got 3 here. I'd like to start with a question for Dr. Hugo. The current system of, can this be considered as an example of digital twins? Thank you. This is for Aldo Quiroga. Thank you for the question. I'm not quite sure because I'm not really familiar with the details of this measurement system with the universal coordinated time. We could imagine that it does comply with being a shadow. You can acquire the data and process them, but I'm not quite sure if there are some mechanisms, feedback mechanisms that will alter or change the behavior of the physical clocks. That would be the twin. So to change it through a command, virtual environment or software control to be able to change the physical counterpart. If that happens, then they are digital twins. I'm quite clear that everything else is being complied with. The only thing I have a doubt about is control of the virtual environment, or by the virtual environment of the physical. Jose Arieta, the next question is, hello, how do you measure or validate the data quality for decision making or for making adjustments in the real model? And that is about data that is provided by the digital twin. Yes, hello, thank you very much for the question. It's an interesting one. In fact, and I'm going to speak in Spanish, what we need to do, and this is why in the presentation we spoke more about metrological aspects rather than technological. The metrological aspect is the basis of all of the technological development, because if we don't have the basis of metrology, any technology might provide incorrect information. So what we did with the models regarding differentials, and this was the variable to be measured, we carried out over 100 measurements of different models and developed parameters determining what the normal operational levels were, comparing good models and bad models in this case. And since we already have a criteria, we established some thresholds in order to determine, well, if it's within those parameters, the mechanism is good, but if it goes beyond those parameters, it would be necessary to check the assembly or check a certain area where there's some error. So when we're talking about the digital twins and the simulations that these programs can run, these are fed basically by the data that we provide to them. And this is what I tried to explain in the presentation. We provided the parameters for the digital twin. And what the digital twin does is to take this knowledge and replicate it in a digital system. So if our data that we've entered are incorrect, then the data of the digital twin will be incorrect. This is why it's so important, the metrological aspect and metrological assurance. Finally, if any of you or any of the presenters would like to answer the final question, which is this digital system approved by standards? I don't know if you would like to comment on this, do you, or any of you, if you have any knowledge about a standard that refers to this. Well, everything that we developed was based on standards, but